Hey everyone, welcome back to The Explainer. I'm your host, Dr. Chem, and today we're taking a highly visual, totally cinematic journey into the seemingly magical world of iron oxide nanoparticles. We're going to crack open the nanotech toolkit that scientists use to build these microscopic marvels from the ground up, and we'll be checking out all the experimental methods in a really attractive, structured way. So let's just get right into it.
Here is our roadmap for today's Explainer. We're covering 1. The magic of magnetic nanoparticles. 2. Building at the nanoscale. 3. The wet chemical toolkit. 4. Advanced synthesis techniques. And 5. Perfecting and protecting particles.
All right, let's kick things off with Section 1, the magic of magnetic nanoparticles. Before we get into the how, we really have to ask, why do we even care about these tiny things in the first place?
Well, as you can see here, iron oxide nanoparticles are literally the invisible engines of our future. Thanks to their incredible properties, they're driving massive leaps in totally different fields. Over in biomedicine, they're working as MRI contrast agents and targeted drug delivery vehicles. In electronics, they're the secret sauce for high-density magnetic data storage. And it doesn't stop there. They're even breaking new ground in agriculture as nanofertilizers and in the energy sector with next-gen solar cells and batteries.
Which brings us nicely to Section 2, building at the nanoscale. Because, honestly, the challenge here is immense. We aren't just snapping Legos together. We're actively controlling atomic reactions.
And one of the most fascinating phenomena at this scale is superparamagnetism. Imagine a material that displays incredibly strong magnetization the second you put it in a magnetic field. But the absolute instant you take that field away, boom, zero residual magnetism. It's totally inert. But here's the catch. Mastering the precise size and shape of these nanoparticles is absolutely critical to unlocking that behavior. If your particle grows even slightly too large, it just reverts back to regular bulk magnetite and you completely lose that super property.
So the whole game is figuring out exactly how to make them perfectly uniform. That takes us to Section 3, the wet chemical toolkit.
The most foundational go-to approach is the co-precipitation method. It's an incredibly common and beautifully simple 1-2-3-step process. First, you mix iron 2 and iron 3 salts right into an aqueous solution. Second, you drop in an alkaline base, like ammonium hydroxide. And third, you precipitate out Fe₃O₄, pure magnetite nanoparticles. It is highly accessible, super low cost, and gives you large quantities of nice, roughly 26 nanometer spherical particles.
But as always in chemistry, scaling things up is where the real headache starts. Look at the trade-offs here. On the left, we've got traditional batch synthesis. It's simple, it's safe, and it happens in a closed system. Just think of a single reaction beaker. But trying to perfectly reproduce your particle size from batch to batch is notoriously difficult because the mixing just isn't uniform. Now, on the right, look at continuous flow synthesis. This is an open system giving you ultra-precise control over nucleation and growth, plus a potentially unlimited yield. It requires way more complex equipment, but you can clearly see why large-scale industrial applications absolutely rely on it.
And this desperate need for extreme precision launches us right into Section 4, Advanced Synthesis Techniques, where chemists take total control over a particle's fate.
Okay, this is one of my absolute favorite methods for continuous flow, using what we call reverse micelles. Picture tiny, localized droplets of water wrapped up in a nonpolar surfactant envelope, just floating there suspended in an oil phase like cyclohexene. They essentially act as microscopic water balloons serving as tiny individual reaction chambers. By dialing in the exact thermodynamic size of these droplets, you strictly dictate the final size of the nanoparticle growing inside it.
To really connect the theory to the real world, check out the schematic on the left compared to the actual digital image of the lab setup on the right. You can literally see how the micellar solutions are precisely pumped by syringes through very specific zones. They pass through a heating zone, get injected into a mixing chamber using ultrasound, and finally glide through a cooling zone. It's an elegant, flawless way to separate and time the nucleation and growth phases, which gives you incredibly uniform nanoparticles.
And the advanced toolkit is packed with other incredible techniques. You've got the Sol Gel method, which uses an eco-friendly water solvent to cultivate these intricate, distinct honeycomb structures. Then there's thermal decomposition, relying on the intense heat of high-temperature pyrolysis to forge perfectly uniform crystals right in that sweet spot of 6 to 30 nanometers. Or, if you want to skip surfactants entirely, electrochemical methods let you dictate particle size just by tweaking the electrical current density.
But honestly, the most mind-blowing extreme in our toolkit has got to be the sonic chemical approach. We're talking about blasting the solution with power ultrasound to induce cavitation. That's the formation and rapid collapse of microscopic bubbles. And when I say collapse, I mean violent collapse. It generates localized temperatures of around 5,000 degrees Celsius. That is nearly as hot as the surface of the sun. And that insane heat drives incredibly fast chemical reactions, giving us extremely narrow size distributions of just 4 to 8 nanometers. Absolutely wild.
Of course, after all that, we have to prove we actually built what we intended to build, right? That's where X-ray diffraction, or XRD, comes in. By matching these exact peak angles you see here to known crystallographic data, we can confirm without a doubt that we've successfully synthesized pure magnetite with its signature inverse spinel crystal structure, and not some unwanted phase like magamite.
All right, finally we arrive at Section 5, perfecting and protecting particles, because the reality is, raw iron oxide alone usually isn't tough enough to survive the real world.
Which brings us to the elephant in the room, bridging raw chemistry directly to human biology. How on earth do we safely put these naked nanoparticles inside the human body for an MRI scan or to deliver a drug? Because raw magnetite will easily oxidize, agglomerate, or just straight up corrode in low pH environments inside us. We urgently need a way to stabilize them.
The most elegant solution is building core shell structures. We literally wrap that magnetic iron oxide core inside a protective outer jacket, usually made of silica, gold, or silver. This shell is a physical barrier. It protects the magnetic core from low pH corrosion, stops the particles from clumping up, and makes the whole thing completely biocompatible. Plus, remember that intense sonochemical method we just talked about? Scientists can actually use that to coat these particles with silica way faster than normal, which stops the magnetite from oxidizing while it's being coated.
And when you zoom back out to the human scale, it's just amazing how well this works. As you can see, once they are properly sized, usually creating core shells a bit larger than 10 to 15 nanometers, and fully protected, they can safely circulate right through our bloodstream. They do their medical job, and then they are naturally broken down by the body's phagocytic system, integrating completely harmlessly into our own natural iron stores in the liver and bone marrow.
So I want to end today's explainer by leaving you with this profound question to chew on. How will mastering the invisible world ultimately reshape our visible one? Because when we really understand this diverse cinematic toolkit, from a simple co-precipitation all the way to 5,000-degree cavitation bubbles, we are gaining literal mastery over the nanoscale. And it's exactly that level of precision chemistry that is going to unlock the next massive revolution in medicine, energy, and far beyond. Thank you so much for joining me on this deep dive. Keep learning, and I'll see you in the next explainer.